Hi everyone, today I'm going to present my work on second life batteries for electrical grid using OPAL-RT simulator. My name is Ali Hassan. So the main idea is to use the retired batteries from the electrical vehicles into electrical grid. So we all know that the EV batteries after a certain amount of use are retired from the batteries. Most of the EV manufacturers recommend that the batteries should be retired from the EVs when their capacity reaches 80%. The thing is that at 80%, the battery has enough juice left in it, although it is not suitable for the EVs, but it can be put to a second life use, and the most appropriate use for the retired EV battery is as an energy storage for the electrical grid, and it can be used up to like 30%, and after that the battery can be totally retired and can be recycled for the rare earth minerals like lithium and cobalt and manganese. So why actually we should use the batteries for a second life? According to one estimate, the retired batteries are going to reach up to more than 200 gigawatt hours by 2030, as can be shown in this, as is shown in this graph. And also, according to one estimate, energy storage system requirement for the grid is expected to increase like 10 times over the next 5 to 7 years. Now, both so there is a supply of retired batteries, and then there is a demand for the grid storage. So repurposing the retired batteries for the grid is a sustainable choice from the perspective of climate change as well as carbon dioxide emission reduction. Now, our work presents an idea that we use PyBEM, which is a Python-based simulation package, to run asserted life testing for the retired battery pack. And then as step 2, we perform a degradation-aware optimization of the second life battery energy storage system scheduling. And then we integrate that battery energy storage system into our microgrid through Simulink by modeling it through Simulink. And then we test the results on OPAL-RT digital simulator. Using and then as a step 4 we run it on the OPAL-RT, and at step 5 we analyze the results, and we try to estimate the amount of carbon dioxide reduction over the next 5 years that our proposed model will provide. Now the step 1, as shown in the previous figure, was PyBEM based degradation. So PyBEM again is a Python based simulation package, and we perform different experiments on lithium-ion NMC battery pack from Nissan Leaf. So actually we are not performing hardware experiments, but we are performing the software experiments in PyBEM, and we are getting different so we are performing different experiments on the battery, and we get different degradation data. And then on the basis of that data, we train an artificial neural network, and we get degradation results, as well as we get an optimized scheduling of our second life battery energy storage system. Now the next step is to perform the optimization. So we use PyOmo in Python for the optimization, and the solver that we use is a Cplex solver. So it's a mixed integer linear programming. So this part here will maximize the revenue from the battery energy storage system, but the second part here is what I refer to as the degradation aware part. So this will also cater to the degradation of the battery. So we don't want a battery to lose its capacity very much fast, and these are the constraints that we subject our optimization problem to. Then we simulated a microgrid in Simulink. So the microgrid has our battery energy storage system, then it has the power supply from the grid, and then also there is a diesel generator. So this is a one Simulink model, but because of the lack of space I divided it into two. And so this is our microgrid in which our second life battery energy storage system will work in. And then there is an OPAL-RT simulator in our lab that we used for performing the real-time simulations. So we used the amplifiers, AC and DC amplifiers, and the simulator, because it's a three-phase system, so we needed 3 AC and DC, 3 DC amplifiers. These are the results from the grid loads, battery loads, and the cumulative power. So this is how the power from the grid looks like for our model, and this is how the battery power would look like, at different points of time, how the battery is going to give the power to our load, and this is how the peak shaving process will work. This cumulative power shows that, graph shows that. And then the main thing, the CO2 reduction calculation. So so our model is going to save CO2 emissions or reduce CO2 emissions two ways. Number one is like we are using our retired batteries. That would certainly create a circular economy for the EV batteries, which will result in carbon dioxide emission reduction. And the second way it is reducing the carbon dioxide emissions through the use of energy storage in the grid. So when we use energy storage in the grid and use it to perform different grid services like peak shaving, then this will require less conventional generation for the base load, and that will also result in CO2 emission reduction. So based on our calculations, I will present like how much metric tons of CO2 our model will reduce. So according to Swedish Energy Agency, medium range 80 kilowatt hour EV battery has a carbon footprint equivalent to 10.2 metric tons. That can be actually referred through this article here. So since we are putting our battery pack of 80 kilowatt hour exactly to a second life use, and using it for another 40% capacity, and retiring it at 40%, then it means that according to this calculation, we are saving around 4.2 metric tons of CO2 emission for one pack. And moreover, like from microgrid perspective, because we are using the second life battery energy storage system for the peak shaving, then the amount of thermal generation that's required for the base load, normally thermal generation is used for providing the power for the base load, that amount will reduce, because now the energy storage system would be covering the excessive load or the peak load. Now that according to our very conservative calculations, we can save save around 5 metric ton of CO2 emissions per year. So that makes like 5 plus 4.2, 9.2 metric tons of CO2 per year. And if you multiply that 5 with 5, that saves us around 46 metric ton of carbon dioxide, per 5 years. So that was our model, and we proposed this model to reduce the carbon dioxide reduction, and that these are the results for the carbon dioxide reduction. Thank you so much.